Okay. Hello, everyone. Welcome to NCSGS. And the first talk today will be given by Tony Bloch on total positivity, gradient, and Hamiltonian flows.
Okay, thanks, Michael, and everybody for the invitation to talk here. So this is a talk on some recent work that I've been doing with Stephen Kopp, who's an expert on positivity and combinatorics. And the talk is sort of somewhere at the intersection between total positivity, combinatorics, and dynamics, and in particular on its relationship to gradient and Hamiltonian flows. So this sort of arose somehow because of some discussions that I had with Stephen, where we realized there was some intersection between work that we've been doing on totally positive Grassmannians and work that I'd done a while back on gradient flows on Grassmannians using different metrics, but also on their relationship with certain Hamiltonian flows and convexity of the moment map. So you'll see there are all these different pieces which I'm going to try and put together. And I'm more expert on some of them than others, but I'll do my best to answer any questions. So this is the broad scope of it. So I'm going to talk a little bit about total positivity, which has some interesting historical roots. I'll just say a little bit about that. And in particular, I'll talk about the role of positivity when we have flag manifolds or adjoint orbits. And you'll see that the total positivity in this case is related to the dynamic that I mentioned. And in particular, it's interesting both to look at flows that preserve this notion of total positivity, which I'll describe, but also these have interesting sort of applications, and in particular to relate to some work that Stephen Kopp did with Galashan and Lamb and other people on the topology of totally positive Grassmannians, for example, and more general flag manifolds. And it turns out that they use these flows to show certain topological results, but viewing things in the context that we do here, we can see that they're interesting gradient flows on a flag or an adjoint orbit, but also viewed via the twist map, which we'll see is related to the dressing transformation that, for example, Alan Weinstein has looked at. You can view these sort of Hamiltonian flows also as gradient-like flows. And in particular, it turns out to be related to the total lattice flow, which is, of course, a famous integrable Hamiltonian system. So at the bottom here, I put a little bit of what was the inspiration of my original work in this area and some of our more recent work, which was going back to some work that I did with Tudor Rachu and Herman Flaschker on the total lattice flow. We observed you have this Hamiltonian flow corresponding to the total lattice flow, and I'll describe this in a bit more detail. But this is a flow on tridiagonal matrices. And if you map the set of tridiagonal matrices with positive off-diagonal entries, this is sometimes called the Jacobi matrix, you could actually view it as a sort of flow on an adjoint orbit. But when you map it to the natural images of the momentum map, instead of getting a full convex polytope, which you see on the left here, you get a map into the interior of this polytope, which consists of these two quadrilaterals, which are joined together at the bottom of the picture. And we wondered if there was a better relationship between the set of tridiagonal Jacobi matrices with fixed spectrum and the momentum polytope. And it turns out that there is, if you use Atiyah's convexity theorem, and it turns out also to be related to some interesting ideas from total positivity. So that's part of the inspiration here, and I'll describe a bit more of that as we go along. So let me start off by saying a little bit about totally positive matrices. So they have an interesting history, which goes back to the 1930s. And you know, I'm not an expert in the history, but as I understand it, it goes back to work of Guntmacher and Krein in particular, and Schoenberg. So the Guntmacher-Krein work, it appears in this book that they wrote and in various papers, was on vibrations of mechanical systems, small vibrations of mechanical systems. So you can think of, you know, if you like, a discrete version of particles on the line, which is related to Toda, or a rod, for example. And it turns out that the matrices associated with these linearized nonlinear systems are totally positive, and so they investigated this in detail. There's a more mathematical inspiration about diminishing sign changes in the sequence. This goes back to a conjecture of Polyer, actually, and this was worked on by Schoenberg, and the idea was to look at matrices A acting on a sequence. You have a vector which represents a sequence, and you look at the number of sign changes in the sequence, and the idea was to look at how to diminish the sign changes in the sequence, and it turns out that the kinds of matrices that do that are totally positive or related to totally positive matrices. And then there were lots of other applications to statistics, Markov processes, and so on, stochastic processes in general. And there's a nice book of Carlin which describes some of these things. So that's a little bit of the sort of early background. More recently, back in the 90s, the flowering of interest in this was due to George Lustig. So let me describe that a little bit. So that's more closely related to what we're doing here. So if you look at a complete flag variety consisting of a sequence of nested subspaces in Cn, sort of V1 and so on through to Vn minus 1, this is, of course, a nice geometrical object, and you can view it as the quotient of the general linear group by the subgroup of upper triangular matrices, and you'll see they all play a role here. And where Vk is the subspace defined by the first k columns of a matrix representative in this quotient. And Lustig introduced two interesting subsets of real points of FLNC called the totally positive and totally negative flag varieties, which I'll call FLN greater than 0 or greater than or equal to 0. And I will define for you now. And there, so this was interesting. And we'll work here always basically in GLN or with the Lie algebra AN, but Lustig generalized this beautifully to arbitrary Lie groups and Lie algebras. And pretty much what I say here can be generalized in that setting, and we're still working on certain generalizations of this. And you'll see, for example, Toda again, which I described in the AN setting, can be generalized to all sorts of relevant Lie groups and Lie algebras, both finite and infinite dimensional. And this is related to some work of Costant. So let's make the connection firstly with the totally positive matrices. So GLN greater than 0 is the subset of all totally positive matrices. So that's the set of matrices whose minors are all positive. So it's quite a strong condition. Stronger, for example, than a matrix which is positive. So a positive matrix would have all entries which are actually positive, but this is a matrix which, if it has all minors positive, all the entries are positive, but also there are all these conditions that the minors are positive as well. And FLN0 is the image of GLN0 inside this quotient that I just mentioned. And equivalently, you can view FLN greater than 0 as the set of flags which can be represented by an element of GLNC whose left justified minors are all positive. And I'll come back to that issue, and that's sometimes those two things differ slightly. So more generally, for any subset K, of 1 through to n minus 1, we can have a partial flag variety consisting of nested nested sequences of subspaces, and its totally non-negative part is defined to be the image of FLN greater than 0 under the natural projection, which forgets the irrelevant subspaces. So we're interested in both the full flag or the complete flag and these partial flags.
Tony?
Yeah.
Maybe I missed your saying it, but could you go back once to that slide previous?
Okay.
What is a positive matrix?
So a positive matrix is a matrix all of whose entries are positive. A totally positive matrix is a matrix all of whose minors are positive, all minors.
So including the 1 by 1 minors.
Including the 1 by 1 minors, exactly.
Okay.
All right.
And minors are all the square submatrices?
Yes, all the square submatrices. And yeah, exactly. And there are also various generalizations to the square submatrices inside non-square matrices and so on. But yeah, the minors are the square submatrices.
And for the minor to be positive, it means that it doesn't mean just that all, it means that it's determined as positive. Is that right?
Yeah.
Oh, okay. Mm-hmm.
Okay. So a particular case of interest, and this is the one that was studied first in a way, and this, the case I was first interested in is the case of the Grassmannian, where the set K is just little one element of K. So we can obtain the Grassmannian as just basically it's the set of K-dimensional subspaces in dimension n, and you can look at, of course, real and complex, and that's a nice manifold for lots of different reasons. And so it's the most sort of simple case in a way of a general partial flag variety. And I'll come back to this, but so you can look at the totally negative parts, both the Grassmannians, these general flags, and in addition to that recent work I mentioned, to that earlier work I mentioned, there's all sorts of interesting work recently on this with lots of interesting applications. So the work of Lustig was to representation theory, but there's work in combinatorics, which goes back to Poznikov. There's work on cluster algebras, which is of course important in lots of different areas, including integrable systems. And in particular, also there's been recent work on high energy physics, where some of this work relates to what's called an amplituhedron. I'll come back to that.
Tony,
yeah.
Can you say the simplest case for the totally positive Grassmannian is not equal to the Grassmannian?
Sorry, say what was that quick? Sorry.
What are the smallest K and N for which the totally the positive Grassmannian is not everything?
Oh, it's not every, that's true, I think, in all cases. So if you just take the regular so I can take the regular Grassmannian for any K, I can look at projective space. So and you'll
K equals 1?
Yeah, even K equals 1, right? So the positive projective space is still not the same as projective space. So, and it divides into, there are various sort of cellular decompositions which one can try and understand, and which I know a little bit about. So yeah, I might come back to that issue. So the other thing is you can view, so there are all these applications. So I think part of the recent work was inspired by this work in high energy physics, but also in topology. But the point is that the totally positive part of a Grassmannian tends to be simpler than a full Grassmannian. Of course, the full Grassmannian is a complicated object, particularly if you look at what its cell decomposition. You use these Schubert cells, and you can look at there's something called the matroid decomposition. But if you look at the totally positive part, it turns out it's either homeomorphic or diffeomorphic to a ball, and that was part of it. But that was unknown for a long time, and some of the recent work of Galashan and Lamb and Kopp actually showed this, and our work is related to that. So you can view a partial flag variety also as an adjoint orbit of a Lie group, and this is sort of the connection with some of the things I'm interested in relation to dynamical systems, and in particular Hamiltonian systems. So, so just to make that a little more specific, so these are the two main inspirations for our work. As I said, it comes partly from this topological analysis of totally positive objects, and partly from dynamics. So on the one side, there's this work of Galashan, Kopp, and Lamb, and what they did is they constructed a contractive flow on a totally non-negative partial flag variety in order to show that it's homeomorphic to a closed ball. And by this way, I should distinguish, we might have something that's positive or totally non-negative, which is, I'll come back to this, greater than or equal to 0, as opposed to strictly greater than 0. And so this was a conjecture which they answered in a very nice way, and it used dynamics. And one of our goals was to try and understand these flows in a more geometrical context. And we'll see that these contractive flows are gradient flows in the Kähler-metric on an adjoint orbit. And as I'll come back to, and I'm sure many of you know, there are various metrics you can write on adjoint orbits. It turns out the Kähler-metric, in some sense, is the right one here, although there are other metrics which are of interest in the dynamical context, which I'll discuss. And then the second inspiration, as I mentioned, was my earlier work with Herman Flasker and Tudor Rachu, where we studied the tode of flow on an adjoint orbit. And the interesting thing about this is that, so the tode of flow, of course, is a Hamiltonian system, but it can be also viewed as a gradient system if you look at it in the right way. And there are two ways to do this, actually. You can either think of it as a gradient flow in the Kähler metric after a certain transformation, namely the dressing transformation, or you can view it directly as a gradient flow with respect to the so-called normal metric. So it's sort of gradient in a certain sense, as long as one looks at the tode of flow, which is what's called the finite tode of flow, rather than the periodic tode of flow, which of course can't be a gradient flow. So one of our ideas here was basically to relate this to these flows that Galashan, Karp, and Lamb used, and relate it to total positivity. And you'll see, in fact, that this is also very natural in another sense, in the sense that the very natural, totally positive object is the set of tridiagonal matrices which naturally arises in toda. So it's quite natural when you sort of look at it in the right way. And here we introduce a generalization of an involution that Galashan, Karp, and Lamb used, called the twist map. And this is related to some work that we used earlier, and a similar sort of mapping that I'll describe to you. And so, as I mentioned, there are these different metrics, and we look at the flows in the Kähler, the normal, and the induced metrics. And one of the questions that we looked at was characterizing which gradient flows are compatible with positivity. And it turns out that the Kähler one is the one that is. The normal metric, which is the one we originally looked at, isn't in some sense. And the other metric, which is natural, this induced metric, is a little more complicated, and we don't actually fully understand that right now. And as I said, we also relate this a little bit to these so-called amplituhedra, which are these interesting generalizations of Grassmannians, and to the symmetric tode of flow, which is a full tode of flow. So you can look at the tode of flow either on tridiagonal matrices or on full matrices, and they're both interesting and both integrable. Okay, so let me just say a little bit. So what I'll do is just describe some of these connections in a sort of broad way. And if I have time, I'll go into some more of the details of the maps and the proofs and so on. So let's first look at adjoint orbits. So as I said, everything we do here really is GLN or U of n. So I want U of n to denote the group of n by n unitary matrices, and little u of n, it's Lie algebra. And I fix a weakly decreasing sequence of numbers, lambda 1 through to lambda n, denoting the eigenvalues of a matrix. And I let O lambda denote the adjoint orbit, which we get simply by conjugating the diagonal matrix lambda 1 through to lambda n, or I lambda 1 through to I lambda n. And you can identify O lambda, as I mentioned earlier, with a partial flag variety, where k depends on the multiplicity of the entries of lambda. So if they're all distinct, you end up with a full flag or the complete flag variety. If you only have two eigenvalues, you basically end up with a Grassmannian. So those are the adjoint orbits that we want to look at. As I said, if in the generic case, where lambda is strictly decreasing, then we have the full flag. And at the other extreme, if lambda is just, for example, all ones and all zeros, we get the Grassmannian. But the other nice thing about it, and you'll see this plays a role in what we talk about, is that O lambda consists of matrices IP, such that P is a projection matrix of rank K. And in particular, for example, if it was rank 1, you just have projective space. And the totally negative part of this object is a corresponding subset, the totally positive orbit, and or totally non-negative orbit of an adjoint orbit. And that's one of the things we wanted to try and understand, and how it relates to totally positive matrices. Okay. So here's the first result, and this is related to some of the things I've already mentioned. So let's fix it. Let's take such an orbit. with so an element IL in O lambda. So then if I take the eigenvalues all distinct, lambda 1 and so on through to lambda n greater than 0, you can check that IL is in the totally positive orbit if and only if L is eventually totally positive. And this plays a role in total positivity. So L doesn't have to be itself totally positive, but some power of it needs to be totally positive. And these sort of eventually totally positive things do play a big role. For example, all the way back to this work of Schoenberg on these sequences where you have objects acting on a vector. So that's sort of a natural object and so on in some sense. Then if lambda is equal to omega k, so one of these Grassmannian type things, then IL is in O lambda greater than 0, a totally positive orbit, if and only if all the k by k minors of L are real and positive, or respectively non-negative. So I just need to look at the k by k minors rather than all of them. And this relates a little bit to Plucker positivity. So it's sort of natural in the Grassmannian context. And finally, to get to the tridiagonal context, which is of interest for Toda, then IL is in the positive orbit, if and only if L is real and its entries immediately above and below the diagonal are positive. And this tridiagonal subject, which is the space of Jacobi matrices, is important in general for total positivity and for Toda. So in some sense, that's the natural object. And if you want to look at natural matrices which are totally positive, if you look at a textbook, you'll see the canonical example of these Jacobi matrices and Vandermonde matrices, for example. So those are naturally totally positive objects. And then, as I mentioned, and this is one of the things that connects everything to Poisson geometry, if you like, is the twist map. So there's an interesting involution on FLN0 called what we call the twist map, which is related to the dressing transformation. So if you're given a V in this flag, you can represent V by unique orthogonal matrix G, whose left justified matrices are all non-negative. That defines the G. And then theta of V, the twist map, is defined to be the element represented by the matrix -1 to the I plus J, GJI. So you can obtain that, essentially we're working on U of N essentially by inverting or transposing G and changing the sign of every other entry. And interestingly, this is the operation that's compatible with positivity. So the question you're answering here, but that turns out to be really important, is basically you're asking the question, if I have a positive matrix, what do I do to invert it so it remains positive? So basically it's answering the simple question of, can you take it, is there a suitable inversion which keeps the matrix positive? And it turns out if you use the right combination of signs in front of it, you can get that. And so that's what sort of the twist map does. And it defines an involution on the positive and non-negative flags. And you'll see that come up. So here's an example. The twist map theta sends this object, the matrix on the left, to one on the right. So that's the twist map. And the first guy is positive, and so is the second. And this is, we call it the twist map since it's analogous to some maps introduced by Berenstein, Fomin, and Zelevinsky that played a role in their original analysis of total positivity for Grassmannians and other objects. But in fact, as I said, it is related also to this map that we used earlier for the Toda flow and also to the dressing transformation. So you can obtain a corresponding involution for any generic adjoint orbit. And it sort of looks like what I've just written down here. For a suitable delta n, as I said, it's related to the dressing transformation. So here lambda is the diagonal entry, the diagonal matrix with diagonal entries I lambda 1 through to lambda n. Delta n is the diagonal matrix with diagonal entries with these given signs. And G in UN is chosen so that all its left justified minors are non-negative. And the important thing is that in general, G to the -1 lambda G just depends on, at least depends on G, and not just on the general G lambda G to the -1 of the point of the orbit. And the whole thing here in some ways, the total non-negativity provides a canonical way of selecting the representative G. And this was really important in our work with Flaschke and Rachu, and I'll come back to that on the momentum map. So if you remember my first slide, where we wanted to get a moment map for the tridiagonal matrices, basically, you know, as I said, if you took the momentum map, which you remember, and I'll come back to this for the Scherhorn theorem, if I just take a matrix and I map it onto its diagonal in a simpler setting, that's the momentum map. And if you have a full set of matrices on an orbit, it fills up the whole matrix, and you get it, you know, you map it to an entire polytope. If you're looking at just tridiagonal matrices, you get this, it leaves out sort of polyhedral segments, but you can fix it by using the dressing transformation or taking an inverse of the orbit, but choosing that inverse properly over the entire orbit turns out to be a difficult problem. That was the hard part of our paper with Herman and Tudor. But total positivity gives you a nice natural way of doing that. So that's one of the nice things to come out of this. So now let me go back to the gradient flow aspect. So as I said, we want to study flows which strictly preserve positivity. And the motivation for that, again, was the topological thing. So it's interesting just in general, but it's also interesting to actually prove topological results about the Grassmannians and about these orbits in general. So you want to study flows that strictly preserve positivity, which means the flow sends the positive orbit to another point in the positive orbit in positive time. And we focus here on gradient flows for height functions. So I just take trace Ln for fixed n, and it turns out on an orbit there are these three natural metrics basically, which are discussed, for example, in Atiyah's original paper on convexity and in the book of Bess and so on. So there's the Kähler, normal, and induced metrics. And in some cases, we are able to classify which flows strictly preserve positivity. One case that turns out to be nice is the Grassmannian case, in which where the three metrics are essentially equivalent. And then we have the following classification. So if k is greater than or equal to 2, less than or equal to n minus 2, the gradient flow, trace Ln on this orbit, which is basically the Grassmannian, strictly preserves positivity if only if In is real and Nij is equal to 0 for I minus j not equal to -1, 0, or 1. And so there's this condition here as well, and at least n minus 1 of the inequalities above are strict. So the interesting thing, and it's not quite, and it is again, tridiagonality enters. So somehow basically, if you have trace Ln for a tridiagonal L up to these other little conditions, you get the metric is being preserved. And then the interesting thing is when the orbit is not isomorphic to a Grassmannian, the metrics are different and the gradient flows exhibit markedly different behavior. And we just investigated by looking at them specifically. And in certain cases, we can say a lot, other cases we can't. But in particular for the Kähler metric, where you can get a beautiful explicit solution, you can write down, you can get a complete classification, basically. And so what you can show is that if lambda is weakly decreasing with at least 3 distinct entries, then the gradient flow of L in the Kähler metric strictly preserves positivity if and only if In is a real tridiagonal matrix whose entries immediately above and below the diagonal are positive. So it's sort of dual in a little bit, in a way, to the Toda flow. On the other hand, if you look at the normal metric, and I'll describe these metrics to you in a little bit. So in the generic case, in the normal metric, there are no flows which strictly preserve positivity, which seems surprising. So I mean, this is a little odd in the sense that the normal metric is very nice for Toda. It's a very nice metric, but it doesn't preserve positivity for some reason that we don't understand. And for the induced metric, it's even more complicated. We're not exactly sure when or it doesn't preserve or not, but we can find certain counterexamples where it doesn't preserve positivity. And oddly enough, it depends on the spacing between the entries of lambda, which also seems surprising. So the induced metric is complicated. Anyway, as I said, the idea here is to use these gradient flows to prove results about the topology of these orbits. And this goes back, as I said, to this work of Galashan, Karp, and Lamb, where they show the totally non-negative part of a partial flag variety is homeomorphic to a closed ball. And what we can do here is rephrase their argument in the orbit metric, and in particular using the Kähler metric. And what we show is this height function that I just described for you, this trace Ln, provides a strictly Oppenau function for the flow. And what we can show is that we have a gradient flow on trace Ln in the Kähler metric. And if you take S basically to be a non-empty compact subset of the stable manifold of the global attractor of this flow of trace Ln, then any flow beginning in S remains in the interior of S for all time. And S is homeomorphic to a closed ball. Its interior is homeomorphic to an open ball, and its boundary homeomorphic to a sphere. So you get this. So basically what you do is you use the gradient flow to sort of show you have a homeomorphism to a ball, as long as you stick to the positive part. And in particular, you can show that the orbit, the positive orbit, is homeomorphic to a closed ball, and that sort of recovers this result of the Galashan, Karp, and Lamb, which is true both for the AN series and more general Lie groups. And one of the other things that we did is apply it to amplituhedra. So I'll say a little bit more if I have time at the end about this. So amplituhedra are the fascinating things. This was introduced by Arkani Hamed, who's a theoretical physicist at IAS and Trinka, who I think actually might be at Berkeley, I'm not sure. And anyway, this was in order to give a geometric basis for calculating scattering amplitudes for supersymmetric Yang-Mills theory. So I think the idea, and I don't understand all the details by any, or even some of the details, but just broadly speaking, the idea is to look at, in particle physics, you're often computing amplitudes for scattering. And their idea was to try and get a more geometric idea of how to compute these amplitudes without going through some of the complicated computations that you have to make in quantum field theory. So this is still an ongoing thing. And one can show that these, and the natural thing that arises are these non-negative Grassmannians and the generalizations, which are called these amplituhedra. And some of those people understand the topology for, and others they don't. And so a lot of this recent work is focused on the combinatorics of the topology, and it's believed that every amplituhedron is homeomorphic to a closed ball. And there are certain special cases where this is known to be true, the so-called cyclic polytope. There's a family of cyclic symmetric amplituhedra and so on. And we were able to find another, just out of this work and using the height function, we were able to find another couple of interesting cases. So, and in fact, so we call these twisted Vandermonde amplituhedra. And these are ones for which the matrix Z, so there's a matrix Z associated with the Grassmannian, arises from applying this twist map that I just mentioned to a Vandermonde flag, which is a flag, which is basically just a Vandermonde matrix. So we can show that putting these things together, that every twisted Vandermonde amplituhedron is homeomorphic to a closed ball. So this gives an interesting new class of amplituhedra, which is kind of nice and sort of unexpected in a way. And then the final sort of piece of all of this is the so-called symmetric total flow. So as I mentioned, the original inspiration for this in a way was the total lattice. And I'll describe that in a second, which is just particles on a line. It corresponds to tridiagonal matrices. And you can show that's equivalent to a gradient flow, but in fact, you can generalize this to a flow on full symmetric matrices. And using some of the techniques here, we can also show that that flow is in fact equivalent to a gradient flow, and which also weakly preserves positivity. So in the tridiagonal case, you can show total flow as a gradient flow in the normal metric, which I just mentioned. That was in our original work. But in the general case, it's a twisted gradient flow on symmetric matrices. And again, you can show it preserves positivity. So So as I said, this sort of generalizes our result where we were interested in this convexity theory. And as I mentioned, in that case, we had this twist map, which basically was the main content of our paper. But this total positivity gives you another very nice and natural way to define this mapping and see that you get a gradient flow and a natural, when in fact, that you can show that the triadiagonal matrices naturally arise from the action of a torus and get the map onto a convex polytope. Okay, so I'll say a bit more about Toda and so on. So are there any questions at the moment? So that's the general overview of everything, and then I'll just fill in some of the details depending on how much time goes, in particular looking at the flows. Okay, well, let me say something about Toda because it's fun to look at. So I'm not sure, people here may know this, but anyway, so let me describe some of it and a little bit of relation to this work. So basically, it goes back again, rather like, the earlier work that I mentioned on continua and so on of Guntmacher and Krein, of just particles on the line oscillating. So this is the Toda lattice. So this is in particular, it's the finite Toda lattice due to Moser. So it's n particles moving freely on the x-axis and interacting under an exponential potential. That's one way you can think about it. So there's a Hamiltonian, which is just sigma from I equals 1 to n of yk squared, the momentum squared, and this exponential potential e to the xk minus xk plus 1. And in some sense, that's where the positivity arises, right? E to the anything is positive. So the associated Hamiltonian equations are simply x dot k equals yk, and yk dot equals dh by dxk, and you get this difference of exponentials. And so this goes back to Toda, who was looking at it as a model for solids. But there's this particularly nice version of it, which is due to Moser, where one takes, you can think of an infinite lattice, which you pull in from infinity. So we use the convention that e to the x0 minus x1 and e to the xn minus xn plus 1 are both equal to 0. So basically, it sort of takes the particle at one end and the particle at the other end and sends them off to infinity in some sense. And that's what Moser calls the finite Toda lattice. So it's a finite lattice, but it represents, in some sense, an infinite lattice. And there was this beautiful transformation due to Flaschke, where he shows if you take the following change of variables, I said ak equal to a half e to the xk minus xk plus 1 over 2, and bk equals minus yk over 2. You get these equations, which are then a discrete set of polynomial equations, if you like, with the boundary conditions a0 equals an equals 0. But more importantly than that, you can write it in the lax pair form, which of course is classic for integrable systems. And the matrices appearing in this lax pair form are tridiagonal. So L is exactly a Jacobi matrix in the sense that I just described. So we have B's on the diagonal, which are positive. They're the momenta. The A's on the off diagonals are positive since they're exponentials. So this is a Jacobi matrix. And in particular, since it's a lax pair, the spectrum is preserved. So if you look at the flow, it's a spectrum preserving flow for L. And the integrals are just the traces of the power of L, which is equivalent to preserving the eigenvalues. And so there are all sorts of interesting generalizations of this to arbitrary Lie algebras. And you can think of a rigid body also on a Toda orbit. This relates to some work I did with Francois Gay-Balmaz and Rachu, where you can give it a sort of inertia matrix as well, and you get an interesting system, which is not that well understood. But this system is well understood in lots of different ways. And there's lots of interesting structure in it. And in particular, there's the following. You can show that if n is a diagonal matrix, diagonal 1, 2, 3 through to n, you can write the Toda flow in this double bracket form, L dot equals L bracket n. And that's, you can easily see that. So there's this B matrix here, which is basically, it's the skew symmetric part of L in the decomposition into upper and symmetric matrix, at least upper and skew symmetric matrices. And you can just, if you literally just take the bracket of L with n, in the 1, 2, 3, and so on through to n, you get this matrix B. So this produces the tode of flow in this double bracket form. And why do we care about this? Well, this turns out to be exactly the gradient flow of the function trace Ln that I mentioned earlier with respect to the normal metric. And that turned out to be interesting, well, firstly, because it's a flow that's both sort of Hamiltonian and gradient. And in addition, it's easy to show things like the following. The flow tends asymptotically to a diagonal matrix with the eigenvalues on the diagonal. So it sort of gives you the eigenvalues, and moreover, they're sorted or ordered according to magnitude. And this recovers these observations of Moser and Symes. And so here's just an example. This is 4-dimensional Toda. So the Hamiltonian takes this little form here, quadratic. These are the equations of motion in this case. And you can compute the flow of trace Ln, and you can check, so it goes very rapid. It just dramatically sorts the eigenvalues. So whatever sort of set of eigenvalues you start off, as long as you're not at a diagonal, it sort of quickly sorts them into increasing or decreasing order. And then there's also this interesting relationship which plays a role in our work, which is the following, and it also relates to Moser. So the idea is, so this is, it's tridiagonal matrices, but the rather fascinating thing is tridiagonal matrices are naturally related to projection matrices, or to the special case of the Grassmannian that we represented earlier. So this is sort of implicit in the work of Moser. It's related to some work of Tomei, but it sort of plays a key role here. So if you looked at that flow, it's a flow on these tridiagonal matrices L, which preserves the eigenvalues. And those, as I said, in some sense are the integrals. So you might try and make a transformation to the eigenvalues together with a set of conjugate variables. And you can do that. So the idea is you represent the flow in the variables lambda1 through to lambda n and r1 through to rn, where the lambda I are the top components of the normalized eigenvalues of L. And you can show there's a one-to-one map between the variables A1 and B1, and you can construct it explicitly going both directions. It's sort of quite interesting, even though you have to do it recursively in the one direction. But then you can show the flow can be written in this, again, in this double bracket form, where now here P is a rank 1 projection matrix, and lambda is the set of eigenvalues. And this turns out to be a flow on a simplex if you project it. And you can map this to a convex polytope via the momentum map. So, so in particular, there are a number of different polytopes floating around here, but in particular, this relates to the polytope that I showed earlier. If I project onto the diagonal for L, I get this Scherhorn polytope, which is a hexagon. If I'm on projective space, then I get a simplex. And more generally, if you look at Grassmannians, you get hypersimplices. So there are a lot of interesting polytopes which sort of float in the background here. And now let me say a little bit about the metrics. So as I mentioned, this double bracket flow is a gradient flow with respect to the normal metric, which is a beautiful metric. So let me just explain that. So as I said, you can think of this as AN, but you can write it for any Lie algebra. It doesn't really matter. But basically, if I have an element L of the Lie algebra, I can decompose any element of L, any element of the Lie algebra, I should say, into something that commutes with any given matrix L, and it's perpendicular. And so if I denote by x lower L, anything that commutes with L, and x upper L, the orthogonal projection, I can break up any x into two pieces, x lower L and x upper L. And if I want to look at a flow on an orbit, the tangent vectors of the orbit are just brackets, L bracket x and L bracket y. So if I'm at the point L in an orbit, a tangent vector is L bracket x. And what the normal metric does is it just pairs x super L with a y super L. So basically, all you're doing is forgetting the part of x that commutes with L and forgetting the part of y that commutes with L, because they don't really matter. and you pair them together. That's the normal metric. And the sort of beautiful result is if I take this trace Ln, the height function, and I look at it on an adjoint orbit, then the gradient flow, L dot equals L bracket n, is just the gradient flow with respect to the normal metric. So L bracket n, if I just take this normal metric, I get this, this nice gradient flow. And that's quite general. It's nothing to do with Toda in some sense. That's the general gradient flow of the height function. The nice thing about it, it's completely explicit. And in the particular case where you have a tridiagonal orbit, you recover Toda. And in addition, as I mentioned, there are these two other metrics. So, so one of them is, so the most natural metric in a way is the induced metric. So the induced metric comes if you don't do what I just did. If you just do the sort of naive thing, if I just paired Lx and Ly together and take their trace, that's the induced metric. And that seems to be kind of a badly behaved metric in this context, at least, for reasons we don't fully understand. And then also because this is a adjoint orbit, and if you take a compact group, you can identify the adjoint orbit with a co-adjoint orbit. You get the constant Kirillov symplectic structure on the orbit. It's actually a Kähler manifold, and there's also a Kähler metric. And then you can look at the flow with respect to the Kähler metric. And as I said, that turns out to be the right metric for looking at total positivity. So the odd thing is, compared to our earlier work, is the normal metric is very nice for looking explicitly at Toda in the first instance, but it doesn't preserve total positivity. On the other hand, if you look at the Kähler metric, it naturally preserves positivity. So both these metrics play an interesting role. The induced metric is a little less clear at the moment. So let me just say another word about the convexity aspect of it. So here's a picture. So just in 3 dimensions, again, going back to this polytope. So again, if I take a polytope in Rn, which is the convex hull of the permutations of lambda 1 through to lambda n, which people call a permutahedron, I can just look at the map mu, which sends a matrix to its diagonal. And that basically is the moment of the momentum map in the setting of adjoint orbits. And the famous theorem of Schur and Horn is that the map mu sends the space of n by n symmetric matrix with eigenvalues lambda 1 through to lambda n onto the permutation group. So literally onto this. So the nice thing is you can take any point in the matrix, in the orbit, it'll send it into the interior. But if I just take any interior inside the polytope, I can find a set of eigenvalues and a set of diagonal entries that actually is mapped to this point inside the polytope. So it's a one-to-one map. And on the other hand, if I look at the set of Jacobi matrices, this is J greater than or equal to lambda. So this is the manifold of all n with fixed spectrum, tridiagonal, with all AIs greater than 0. Using this map of Moser, which I just mentioned, the map L, which sends the vector of first entries of the normal eigenvalues, which sends L to the vector of the first entries of its normal eigenvectors. This is a homeomorphism onto Sn minus 1 greater than 0. So basically, it's the positive sphere, if you like. So this is this map that I just mentioned. And you can send it to the projection matrix if you look at it in the right way. And the interesting thing, as I showed in the original slide, is that this naive map, which uses Schur-Horn theorem, is neither injective nor surjective. If this is perm, you end up with this interesting set of 2 quadrilaterals, which are joined at a single point. And the original result that we had with Herman and Tudor is that instead of looking at g lambda g to the minus 1, you look at g to the minus 1 lambda g. Then, in fact, you can get a homeomorphism of the set of Jacobi matrices with fixed spectrum onto this convex hull, perm of lambda, and it's a diffeomorphism onto its interior. And the idea is that you have to sort of flip g lambda g to the minus 1 to g to the minus 1 lambda g, and come up with a sort of a map that makes sense across the entire orbit. And that's the complicated piece, which turns out to be nicely solvable or understandable using totally positive matrices. So as I said, so the idea is you make a choice of G and ON, which depends smoothly on L. And total positivity shows a good way to making this choice beyond the, and to generalize it beyond the tridiagonal case, which is what we do here. So are there any questions about that? Okay, so I have a few more minutes, so let me just say
I'll ask a question.
Yeah, sure.
Can you go to the previous slide? To me, the most interesting part about that was the right-hand one, this union of these two little diamonds.
Yeah.
So for higher tota, do you still get a union of convex sets like this of polyhedra if you do the same thing? I mean,
yeah,
if I understand right, your theorem says just look at the orbit of the tridiagonals and project, and you land onto the convex hull. Am I understanding the theorem right?
You mean for the so if I'm not looking at tota, sorry, if I'm
well, let me just back up to the theorem.
Yeah.
Is the theorem saying if I take tota, for example, and then allow myself to act by the rotation group, then I map onto the convex hull?
So yeah, so for tota, so what it basically shows is the set. So what you can show is if you take the set of tridiagonal matrices, what you can actually show is that it turns out to be a torus orbit, and then you can apply the convexity theorem. So if I look at the set of all tridiagonal matrices, tridiagonal Jacobi matrices with fixed spectrum, you can show it's basically homeomorphic / diffeomorphic to this convex polytope. But that uses this twist map that I show here.
But if I look at the little picture to the right, so the difference is you're restricting to positivity. Is that correct?
No. So the difference is if I just naively take the set of, if I take an orbit, so the set of tridiagonal matrices is a particular it's a particular orbit. And if, in fact, if I just go, so I take the action of your view of n on a particular orbit, and in fact, it's the orbit through the point with, say, zeros on, at least through the matrix, with zeros on the diagonal, and ones on the upper and lower diagonal. If I take that particular orbit, it's tridiagonal, and that's a low rank orbit. And if I just do the naive thing, which is project onto the diagonal, which is what Scherhorn tells us to do, then I end up with these two diamonds. So I don't fill out the entire polytope.
So my question is, what if you do that naive thing for a larger, what do the pictures look like for, instead of 3, 2, 1, 5, 4, 3, 2, 1? Yeah,
so no, so right. So if you go, so there are maps. So you can show, so for example, so there are various things you can do. And so this goes back to some work also of Kodama and Lauren Williams. So if you look at the full tota, so there's a symmetric tota and a non-symmetric tota, but there are other interesting maps onto other polytopes. So what are called matroid polytopes. So if you go to higher dimensions, you can still map the flow onto what are called these matroid polytopes. So there's a natural sort of momentum mapping, but you get more complicated polytopes. So
that your example on the top right there is like the simplest matroid polytope that's not convex or something?
I think, yeah, so that may be, yeah, so I guess this, I'm not 100% sure if this is a matroid polytope or not. That's a good question, but I think so. But yeah, so, right, so there are all these other interesting polytopes, and they also glue together in interesting ways. So even, for example, if you take the tridiagonal case and you allow the off-diagonal entries to be non-positive, if you allow them to alternate signs, you can glue them together to get a map to another sort of large polytope. You can glue these polytopes together, and that turns out to be related to what are called aspherical manifolds, which were studied by Mike Davis and other people. So yeah, so in all of these different cases, they're interesting maps, but getting the map is kind of tricky, and to get and to show that the tridiagonal matrices with fixed spectrum are actually diffeomorphic to this polytope requires this more complicated theorem of Atiyah. It uses the Kähler structure, and this convexity theorem, and the naive Scherhorn theorem doesn't quite work. And that's sort of true in general to see what the polytope map looks like. You need these twist mappings.
Thank you.
Okay. So, so maybe, yeah, so I guess I've more or less used up my time at this point. So, yeah, maybe I should stop here. So as I said, so I'll just end up with a few remarks then. So, so just related to what Richard just asked, you can generalize, so that there are a couple of natural, so there are generalizations of all of this, but in particular, as I said, it's interesting. So here I just showed you at the end here, the flows corresponding to Toda, both sort of in the projective space and the Grassmannian picture. You can generalize it to look at total positivity for more general so the more general Grassmannians, and particularly these amplitude hedra, and you can get these nice topological results about these amplitude hedra being homeomorphic to a ball. And as I said, in general, that's open, but there's certain specific cases that we were able to prove. And also you can generalize these interesting results on preserving positivity to more complex Toda flows, and particularly what we looked at here is the symmetric Toda flow, which is a full matrix. So that's much more complicated in some sense, at least from the integrability point of view, because the set of eigenvalues or the traces are not enough to prove complete integrability, but it's still a very nice simple flow. It also sorts the eigenvalues and does nice interesting things. And using this sort of generalization of this dressing transformation, you can again show that it's a gradient flow, not with respect to this normal metric, but with respect to the Kähler metric. And this, again, gives you these very nice properties of the flow, that it sorts and things of that sort. So that's what we're looking at. And there's sort of other interesting aspects, as I said, looking at other generalized polyhedra, at least other generalized amplitude hedra. And we're still looking at the connection with the, certain different types of positivity that I haven't mentioned here, but you can sort of distinguish between certain kinds of positivity as well as something called Plucker positivity. And one of the interesting things here is that certain flows preserve this one type of positivity, but not the other. So there's some interesting little subtleties about positivity preserving in general, in particular, when you don't look at the simple cases. So it turns out in some sense that the simple case to look at is either a complete flag or the Grassmannian, and incomplete flags turn out to be super interesting. And the associated polytopes, the geometry, the flows are really sort of fun to look at, and that's something that we're looking at the moment. Okay, so I'll stop there then. Thank you.
Thank you very much. We've had a bunch of questions, but are there more questions? All right, well, let's thank Tony again.
Okay, well, thanks for the opportunity to talk. It was fun. Sorry I'm not there in person, but it was great to have this remote opportunity.
We'll be happy to see you in person on another occasion.
Yes, I hope so. All right, well, great seeing everybody virtually. Thank you.
I'm going to stop the recording now.